Go ahead and get started. A couple of things worth noting. I'm finishing up that last little part of section 4.3 today on vertical asymptotes, and then moving on into section 4.4. I'm finishing up that one too. That is business application, so more business formulas you guys need to know. However, which means we're in the chapter 4, we're ready for our next test. Now, if you look on the syllabus that I set up, the test is actually scheduled for Friday, but I wanted to make sure you guys had a chance to actually have the famous homework review. So I have printed out for you guys a homework review, and I have also posted it on your Canvas site down here at the bottom. So the way I have it set up, and I want to make sure you guys have the weekend to do this thing, so I'm going to give it to you today, not going to make it due on Friday, which I officially could, but I'm just going to kind of shift some things around. So you guys have the weekend to get the homework set due. So the homework set is due on Monday, March 25th, which puts your test on Wednesday, March 27th. So March 27th is when your test is going to be. Now, the homework is due Monday, March 25th, and we will actually cover this thing in class. So, and here's a copy of this thing. And also, like I said, click on this. You can go right here and click on it, and you actually have the link to it over here. And you can print out your own. But I also have these things actually printed out. So, here you go. And I'll let Son just pass these things out for you guys. Oops. Thank you. There you go. And so here's a copy of it, and I shortened it up a little bit. So this one is pretty much about 17 multiple choice, or 18 multiple choice questions. Oh, especially 19, because I put some graphs on here. But quite a few of them are actually 10-second questions if you know what you're doing, because there's look at the picture and tell me which you want, which is the right answer type thing here. And then over here, I also have just a couple of free response questions. And one of those problems about, here's some information about a particular graph, what does the actual graph look like, stuff like that, which is a problem we did last time and stuff. So this is actually your homework set, and we will be going over this on Monday. You turned it in at the beginning of class, and I'll use this as a great review for your test on Wednesday. Also, if you have a particular question, don't forget, we have set up a review session for you guys every Friday. So it's Friday from 12:30 to 1:45 in Brentwood 113. So if you want to come to this thing and bring these kind of questions to it off the homework set, that's perfectly fine too. We'll take a look at it and see what kind of questions you have and stuff. So, but it is due. So my goal here is this: since it's due on Friday, and I'm finishing up chapter 4 today. On Friday, I'm going to go on to chapter 5. I'm going to do section 5.1 and a big part of 5.2 because I don't have time to waste. I'm going to move on. All I'm doing is putting the test back just a little bit to give you guys some time to actually finish up the homework set, get some soak-in time over the weekend to get prepared for the test and stuff. So there's the big plan. And so, like I said, these are the ones we're passing out. I'm also going to be passing out to you guys. Here is your last homework set. I have not put these things up on Canvas or on the Hawk system yet, but I will be putting that very soon. I've got the Excel spreadsheet, I just haven't uploaded it yet, but here are your grades for your last homework set. So, I passed back one homework set and then pass out a new one, so that's not classic here. All right. So let's go ahead and get started on today's lecture. The first part of it is we're finishing up that last little bit from section 4.3. Chapter 4 only had 4 sections in it. Section 4.3, and we were talking about two things: vertical asymptotes and horizontal asymptotes. Your vertical asymptotes are when you have this. When I have a rational function, so y is equal to, we'll call it f of x divided by g of x. So I have a rational function, which is a polynomial over a polynomial. So on my rational function here, to figure out when you're going to have a vertical asymptote, here's what you have to do. To get a vertical asymptote, you are going to set the denominator equal to 0 and solve. and then check. Here is your check, the thing that you guys need to know. To check this guy, what you're going to do is there's two cases. If you have a case one is you plug in the number, plug in. Let's see, you said the denominator equals 0 and solve. Let's say you get x equals a, just to give me something to plug in here. So you're going to solve and you get a number, x equals a. You're going to plug in x equals a into your function. And if you get a number divided by 0, then x equals a is your vertical asymptote. And it's an equation, x equals a. However, in case number 2, when you plug in x equals a into your function, and you get 0 divided by 0, then at x equals a is a, quote, hole in the graph. It is not a vertical asymptote. Does that make sense? It's a hole in the graph because the idea is that 0 divided by 0 ends up canceling. And if this goes back to that chapter 1 stuff when we were doing all those limit properties and stuff like that. 0 divided by 0 makes holes in the graph. Number divided by 0, anything other than 0 divided by 0, number divided by 0, that means x equals a is your vertical asymptote. And comparison, we also had HA. HA is the horizontal asymptote. And with the horizontal asymptote, we had the horizontal asymptote theorem. So here's the deal. So you've got y equals f of x divided by g of x, and then you basically focus on cases. Case number 1, if the degree of f of x, the top, is less than the degree of g of x, the bottom, then y equals 0 is the horizontal asymptote. Case 2, if the degree of f of x is actually equal to the degree of g of x, then y equals the ratio of leading coefficients is the horizontal asymptote. You basically take the leading coefficient numerator divided by the leading coefficient denominator. That becomes y equals the ratio of leading coefficients is your horizontal asymptote. And then there was the interesting case of case number 3, was if the degree of f of x, the top, is greater than the degree of g of x, the bottom, then there's no horizontal asymptote. You have what we call an oblique or slant asymptote. Okay? And what you have to do there to figure out is you do long division, and y equals what we call the quotient in that long division is the slant asymptote. So, picking it up where we left off last time, we were looking at basically finding vertical and horizontal asymptotes of rational functions here. So, and it was under our practice right here, so let's take a look at this guy. Okay? In all these directions, they pretty much say the same thing, and that is this. Quote, find any vertical and horizontal and oblique asymptotes for any of the following functions. First thing I'm going to start with is I'm going to find the vertical asymptotes. To find vertical asymptotes, this is what you do. I'm basically going to go ahead and take my rational function and go ahead and factor the numerator and factor the denominator and then set the denominator equals 0. And I'm showing you this for a reason. So in this particular problem, look at your numerator. I can factor out a negative out of this thing, a negative 1. I got negative x minus 1 divided by negative 3x squared plus 13x minus 4. I can factor out that negative 1 out of this guy, and I'm left with x plus 1. Because when you factor out a negative, it changes your signs. Divided by, now this particular problem, I can factor out, look at it, it's negative 3x squared plus 13x minus 4 for the denominator. That's a classic quadratic. So you want to do this anti-full thing. But if you look at it, I don't have any terms that are in common. However, that leading coefficient is negative. When I'm trying to factor a polynomial, especially a quadratic, I hate to have a negative leading coefficient. I want to have a positive leading coefficient. It helps me factor it in the old traditional way. So I'm going to factor a negative out of it. Factoring a negative 1 out of it leaves me with a 3x squared, a minus, changes your signs, 13x plus 4. It changes my signs. Does that make sense? All right? But now, here you can clearly see, cleaning it up, the negatives cancel. That's actually nice. So this is equal to x plus 1 divided by, now let's factor the denominator. I got 3x squared minus 13x plus 4. What times what is 3x squared? Well, 3x squared factors into 3x times x. Only one way it can do that. However, the 4 on the last term has two ways of factoring. It can factor in a 4 times 1 or 2 times 2. The goal here is to figure out what do I need to do to get that outer inner on the foiling method to be able to equal to that middle term, in this case, negative 13x. So here's the pattern. Since the last term is positive, I'm going to add up to get that 13. And then I'm going to worry about the signs. So I'm going to multiply one of these numbers by one of these numbers and the other one by the other one, and I want to get 13. Well, 13 is kind of big, so I think I know which way to go. I'm going to multiply the 3x. I'm going to multiply it times the 4, and 3x times 4 is 12x. And then I'm going to multiply the x by the 1. And x times 1 is 1x. And a 12x plus a 1x makes a 13x. So that's the way I got to do it. So my factors are going to be 3x times x, but I want to multiply the 3 times the 4, so on the foiling, the 3 gets multiplied by the 4 over here, and the x gets multiplied by the 1. And now, all I got to do is figure out the signs. Well, since it's a plus, they're going to have the same sign. Because the middle term's a minus, they're both going to get minus signs. And this is how it factors. And the reason why I'm showing you got to factor the numerator and denominator is this. When you have a factor that completely cancels, that's your 0 over 0, which makes holes in the graph. But you'll notice that none of my factors cancel. So to figure out the vertical asymptote, which is what I'm really after here, I'm going to take the denominator, which is the 3x minus 1 times the x plus 4. I'm going to set it equal to 0 and solve. I'm going to set each factor, 3x minus 1 equals 0, and the other factor, x minus 4 equals 0, and solve. And when solving, I'm going to add 1, and then divide by 3, I get 1/3, x equals 1/3. And here I'm going to add 4 to both sides, and I get x equals 4. And for vertical asymptotes, there are always equations. Vertical asymptotes are x equals equations. Horizontal asymptotes are y equals equations. So the answer is x equals 1/3 and x equals 4. I've got two vertical asymptotes for this guy. Does that make sense? But the question asks for, find the vertical asymptote and the horizontal asymptotes. Well, for the horizontal asymptotes, check it out. What is the degree of the top? The top of this guy is negative x minus 1. What's the degree of that guy? Degree is the largest exponent. What's my exponent? 1. Compare that to the degree of the bottom. What is your denominator? What's the degree of negative 3x squared plus 13x minus 4? It's 2. And I notice the degree of the top, which is 1, it compares to the degree of the bottom, which is 2. The degree of the top is less than the degree of the bottom. And according to my horizontal asymptote theorem that I have memorized, when the degree of the top is less than the degree of the bottom, what do we get? Y equals 0 is the horizontal asymptote. So here, this implies that y equals 0 is the horizontal asymptote. And if you got a horizontal asymptote, you won't have many oblique asymptotes. Oblique only occurs when the degree of the top is greater than the degree of the bottom. So here's my answer. I've got x equals 1/3, x equals 4, and y equals 0. Vertical asymptotes and horizontal asymptotes. Does that make sense? Okay? Look at the next one. The next equation is this guy. f of x is equal to 4x divided by 9x minus 9, okay? The first thing I want to do is factor. Well, numerator's pretty nice, it's 4x. But the denominator, I can factor out a 9. That leaves me a net at 9 times x minus 1. And I don't see any terms canceling on this guy, so I don't have to worry about any holes in the graph. So for the vertical asymptote, I'm going to take my denominator. So you take the denominator, set it equal to 0 when you solve. My denominator is 9 times x minus 1. I'm going to set it equal to 0 and solve. I'm going to divide by 9 on both sides, get rid of my constant. That leaves me with x minus 1 equals 0. And I'm going to add 1 to both sides, and I get the equation x equals 1. That is my vertical asymptote, x equals 1. For the horizontal asymptote, I'm going to focus on the degree of the numerator, the top, and I'm going to compare that to the degree of the denominator, the bottom. What is the degree of my numerator, the top? 1. It's 4x to the first power. The degree is 1. What is the degree of the denominator? It is 9x minus 9. What's the degree of it? It's 1. So in this one, the degree of the top is equal to the degree of the bottom. And according to my horizontal asymptote theorem, when the degree of the top is equal to the degree of the bottom, I'm supposed to get y equals the ratio of the leading coefficients. Does that make sense? What are my leading coefficients here? So it's going to be y equals, the leading coefficient on the numerator is a 4, divided by the leading coefficient of the denominator is a 9. The answer for the horizontal asymptote is y equals 4 ninths. Does that make sense? And then, number 3. F of x is equal to 2x squared minus x minus 3 divided by negative x minus 3. So the first thing I'm going to do here is I'm going to factor the numerator and denominator. I focus on vertical asymptotes. So focusing on this vertical asymptote aspect, I'm going to factor my numerator, factor the denominator. By factoring the denominator, I can pull a negative 1 out. That's pretty much it. And I'm left with x plus 3. Remember, when you pull a negative out, it changes your signs. But in the numerator, I've got 2x squared minus x minus 3. So how is this guy going to factor? Well, again, the leading coefficient is not a classic 1. So how does 2x squared factor? It factors into 2x squared, factors into 2x times x. Only one way it can factor. How does the 3 going to factor for the constant term? Only one way it's going to factor is 1 times 3. But now, because the last term is a minus, I want to subtract the outer inner to be able to get the middle term of a 1. So to be able to subtract, I'm going to multiply the 2x times the 1. So multiply the 2x times the 1. That gives me 2x. I multiply the x times the 3. That gives me 3x. And notice the difference between 2x and 3x is 1x, which is what I got in the middle, and then I'll worry about my signs. So I'm going to take the 2x, multiply by the x, and I want to multiply the 2x times the 1. So on the fulling, the 1 will have to go here. I want to multiply the x times the 3, so 3's got to go there. Now, my signs. Because the last term is negative, they're going to have opposite signs. Since the middle term is negative, I want the fulling with the bigger number to get negative. What gave me the bigger number was the 3 times x. I want the 3 to be negative, and I want the 1 to be positive. So I get a positive 2x there and a minus 3x there. That gives me the negative x. Now I look to see if any factor is going to cancel, because if it cancels, that makes holes in the graph, not vertical asymptotes. But nothing cancels here. So to find the vertical asymptote, I'm going to set the denominator equal to 0 and solve. This is negative 1 times x plus 3 equal to 0. I'm divided by negative 1. No problems there. 0 divided by anything besides 0 is 0. So that gives me, this cancels, and x plus 3 is equal to 0. I'm going to subtract 3 from both sides, and I get the answer x equals negative 3. That is my vertical asymptote. Now, what about the horizontal asymptote? We're checking for the horizontal asymptote. I have the degree of the numerator, the top. What's the degree of the top? 2. Compare that to the degree of the bottom, the denominator. What's the degree of the denominator? Negative x to the first, so it's 1. In this case, you'll see that the degree of the top is actually bigger. than the degree of the bottom. So we don't have a horizontal asymptote. This implies that we have what we call an oblique or slant asymptote. Does that make sense? But here it comes. To figure out the oblique or slant asymptote, what you have to do is you got to go back and do long division. And this is all of your college algebra days coming back to haunt you again. Long division. So I'm going to divide this guy. My divisor is the guy on the bottom, which is my negative x minus 3. And my quotient is the numerator, or it can be my dividend, is my numerator, the 2x squared minus x minus 3. And doing my long division, the oblique asymptote is the answer to the quotient part. Okay? So the answer for the oblique asymptote will show up here on the top when you do your long division. But let's remind you guys on how to do long division on polynomials. It's a game. What times, here it comes, negative x is going to be equal to 2x squared. Well, I want to get rid of the negative, I've got 1, and I want to go and get a 2 out of it. I want to multiply it by negative 2, right? Negative 2 times negative 1 makes positive 2. And what times x is x squared? X. So I'm going to multiply this term by negative 2x, and I'm going to distribute. So here it comes. Negative 2x times negative x makes it positive 2x squared. Negative 2x times a negative 3, negative times negative makes it a positive. 2 times 3 is 6x. And they should line up. Now, if you remember your long division, after you match, you do what? Subtract. And subtract changes your sign. So I'm going to come over here and do minus, minus above this and change my signs. And here's the rule. The first term should always cancel, because you really screwed up if it doesn't. The whole goal is to match this stuff up. So this guy cancels. And then you're left with negative 1x minus 6x. What's minus 1x minus 6x? Negative 7x. And then you bring down your next victim, minus 3, and play the game all over again. What times negative x is going to be equal to a negative 7x? Not negative. Negative times negative is positive. I already got the negative there. I just need the 7. So I'm going to put plus 7. Positive 7 times a negative x is going to be a negative 7x. Does that make sense? And 7 times a negative 3 is a minus 21. And now what do? Subtract, which would actually change my signs. So that minus 7x becomes a plus 7x, and that minus 21 becomes a plus 21. And minus 7x plus 7x cancels. Minus 3 plus 21 is plus 18. And in terms of long division, this is called the remainder. This is called the quotient. And when you're talking about the oblique asymptote that we're after, the quotient is the answer. The oblique asymptote is y equals the quotient answer. So my answer is going to be y equals negative 2x plus 7. That is my answer. The remainder is a fraction of the answer. And remember what the horizontal asymptotes and oblique asymptotes do. They tell you what's going on at the ends of your function. So if you actually do the long division on this thing, what you end up getting is the original function, which was f of x, would actually be equal to the quotient, negative 2x plus 7, plus the remainder, but the remainder, which is 18, is a fraction of the answer, and it's 18 over negative x minus 3. And as I talk about what's happening at the ends, at positive infinity and negative infinity, this x is on the bottom. And when you take a limit as x approaches infinity or negative infinity, and it shows up in the bottom, so I'm going to get infinity or negative infinity in the bottom, the overall fraction goes to 0. That's why this ends up being your asymptotes. And just to show you kind of a graph of what's going on here, turn my calculator on. Here we go. I'm going to type this function just to give you an idea of what's going on with an oblique asymptote. You get y equals parentheses 2x squared minus x minus 3 divided by parentheses negative x minus 3. Now, if I do this, I'm just going to do a zoom standard, zoom 6, zoom standard, negative 10 by 10, negative 10 by 10 screen. And you just see part of the graph down here. You see this part. There's another part that's up here, and it's going to be above this. So I can actually go into my window and change the Y maximum. And I'm gonna change the Y maximum to be around 35 or something like that. And if I do that, scale it by 5 or something or other, you'll see the other section of graph. There's a little graph over here, and here's the rest of it. Now, what's going on is this. If you notice this graph, is you've got a vertical asymptote over here at x equals -3, but the thing is going at an angle. It's not horizontaling out. Horizontal asymptote, it goes toward the horizontal line. If I go under y equals and type in that slant asymptote, that oblique asymptote of -2x plus 7, just that part there, you're going to see, you see that line? That is the line that both of these two functions are approaching as x gets bigger and bigger and bigger. This is what the lines are approaching. It's a slant asymptote. Does that make sense? That's kind of the idea there. All right. So now go and finish up these problems. But on these problems, there's quite a few of these kind of questions and stuff like that. Now, the last section on 4.4 is pretty much business applications. And they're going to have one major equation here, one major formula. Now, remember, your life is to maximize and minimize. This is our idea of calculus. And to maximize or minimize, what do? Take derivative, set it equal to 0, and solve. This is how you get your critical values, and then you go analyze those critical values, okay? So, the formulas you need to know. And again, this is just business, so I'm going to go straight into the formulas and stuff like that. So, in this problem, we're going to be focusing on the concepts of applications of business. Basically, our objectives are to determine the price a company should charge for their product in order to maximize revenue. So we're looking at maximizing revenue, because minimizing revenue kind of is stupid. Think about it. Maximizing revenue, how much money you're going to try to bring into the company, okay? And you're also, at the same time, you want to minimize inventory cost. Minimize inventory cost. Well, if you remember revenue is basically the number of units you sell times the price at which you sell them. That was your revenue equation. But this inventory cost and stuff, we're going to kind of basically put these guys together. All right, so, quote, retailers' cost in maintaining an inventory of goods can be considered to be consistent of two categories. And those two categories are storage cost and ordering cost. So again, looking at inventory in your company. All right, when you look at inventory in your company, you got to worry about two things. Number one, I got the stuff. I don't want to worry about how much it costs me just to get the stuff. Let's just focus on the stuff I've got, I would like to sell. Well, if it's not selling, it's going to sit on my shelf. Does that make sense? And so that is that storage cost. But once I run out, I've got to order some more stuff. And it'd be great ordering some more stuff, and of course I'm going to have to pay for ordering that stuff, but I'm also going to be charged an ordering cost. You know, I got shipping and all this other, not just the price of the item, but I've also got the shipping and all these other type of costs, shipping and handling. And that open word handling, I'm sure you guys are familiar with. The prices on that can be also quite interesting. So that shipping and handling aspect from the business perspective, okay? So here comes some of your formulas. Here we go. The mathematical following for the following components. Lot size, what we call lot size is going to be my variable x. That's going to typically, again, focus on this application stuff. Lot size is x. So the average number of items in the inventory is going to be x divided by 2. Okay? Okay, so a lot size, I mean, in terms of average number in inventory, well, if you got X number of items, you want to put some of them on the shelf to sell, and hopefully you'll sell. That'll be your front marketing. And then you got the, basically your big storage stuff in the back, and you can put half of them in the back. So when you run out there and you grab your stuff and you put them from your supply in the back, and you put some more on the shelf. You don't want to run out. Does that make sense? So you basically put half of them up front, and the other half is actually back in inventory that you're waiting until the other stuff runs out, and you get it, and then you start thinking about ordering some more stuff, okay? And the number of orders per year is going to be equal to total ordered, get my word right, total ordered divided by X. X is the number of lot size, and X is the lot size. So let's think about this for a second. Let me read my crappy handwriting here. But it's total order, okay? All right. How much you want to keep in storage? You got some out front and you want to keep some in the back, and we're talking about lot size. X is the lot size. That's how much we actually have on hand. Does that make sense? But I'm talking about ordering per year. So I've got to figure out how many I'm going to have for the entire year that I plan on selling and stuff, and then I want to figure out how much I'm going to actually try to keep on hand at the store, and then the division between the two, the total number that I want to have, divided by the number I want to keep on hand, is going to tell me how many times a year I'm going to have to order this stuff. Makes kind of sense. Does that, you guys good on that? So here comes your big one, okay? Inventory cost can be modeled by, here comes your big equation here, C of X is equal to, and it's such a big equation, I'm going to write it down here. C of X is equal to storage cost per item times X divided by 2 plus cost per order times the total ordered divided by X. And it's a formula. And this is how you get your, quote, inventory cost. You're going to be given some information about the storage cost per item, what it actually costs you to store the stuff, times the X divided by 2. X divided by 2 is actually the amount of stuff you got in the inventory, sitting in the back shelf. Does that make sense? Plus the cost per order, how much does it actually cost you to order this stuff? And then the number of times you're going to be ordering that, and that's the number of orders per year, which is the total order divided by X. This is how you get your, quote, your inventory cost. And it's a formula you guys need to know. So, knowing that nice formula, let's turn the page and let's do some word problems here. This first problem is from our www.hawkstv.com example. Again, go watch the TV example. There's one similar where they change the numbers around, but more examples you guys do, the better off you'll be. And then we kind of change the numbers, and we got this one here. All right. So it says this. Sporting goods store expects to sell 120 tennis rackets during the next year. It costs $4 to store one tennis racket for 1 year. To reorder, it is a fixed cost of $15 plus $4.70 for each tennis racket order. In what lot size and how many times per year should an order be placed to minimize inventory cost? Okay? I want to, at the end of the day, minimize inventory cost. Okay? That's what I want to do. Minimize inventory cost. So, anytime you hear the word maximize or minimize, what are you going to do? Take derivative, set it equal to 0, and solve. That's your goal. And then, always, with any kind of word problem, go back and answer the question. This is the goal here. So, here we go. If I want to minimize inventory cost, you need to come up with a formula for inventory cost. What was my formula? We just wrote it down. It was, quote, the storage cost per item times X divided by 2 plus the cost per order times total ordered divided by X. just recopy the formula we wrote down before. And remind you, X is your lot size, how many you're actually gonna have on hand, okay? So, read through this problem and let's analyze what's what. So, C of X is gonna be equal to, what was my storage cost per item? Let's read through this thing again. It says, a sporting goods store expects to sell 120 tennis rackets during the next year, okay? So, we want 120 tennis rackets. That's what we need to order. Think about it. It costs $4 to store one tennis racket for 1 year. To reorder, there is a fixed cost of $15 plus $4.70 for each additional tennis racket ordered, okay? All right, come up with the equation here. First off, what is the storage cost per item? $4. It costs $4 to store one tennis racket, one item, so it'd be $4. That'll be 4 times X divided by 2. Does that make sense? Plus, what is the cost of reordering? To reorder, there is a fixed cost, so here comes the big one here. There's a fixed cost of $15, that'll be 15, plus $4.70 for each additional tennis racket you order. It costs you $15 to get one of these tennis rackets. Just a fixed cost. If you're going to order it, that'll be your shipping cost, let's say. And then, wait a minute, there's more cost. There's $4.70 per each tennis racket we're ordering. How many are we ordering? No, X. That's the question is, basically, well, actually, you're right. If we want to sit there and look at this thing, we want to sell 120 tennis rackets on this thing, but for each tennis racket that's ordered. Okay, and what lot size? So this is going to be, see, X is going to be in your lot size here. So it's going to be how many lot sizes? So X is the lot size. That's why I put times X. This is how many times. Every time I order, it's $15 plus $4.76 times X. Now, how many total are we going to be ordering this year? How many tennis rackets we want? So this is going to be times total ordered. Our goal is we need to sell 120 tennis rackets. We need 120 tennis rackets. But here's basically what I'm trying to get to you guys is this. Do you actually want to get all the tennis rackets at one big plop, one big sale? I'm going to go out and buy the entire 120 tennis rackets. But my problem is, I do that, and then half of them are going to sit in the back shelf. It's going to cost me money to actually store this stuff until eventually I sell them. Does that make sense? So maybe better, instead of doing it just one time a year, maybe 2 or 3 times a year, is how many times I actually should be ordering this particular stuff. Okay? So the total ordered is 120. X is the lot size. How many I'm going to order each time. Does that make sense? All right. So clean this guy up, and what do we get? C of X is going to be equal to trying to do my problem here. Let's see here. I get the cost per item is 4 times X over 2. That would give me what? 2X plus, in this problem here, I'm going to distribute and grab my handy dandy calculator because I don't want to screw this mess up. Where's my calculator? There it is, over here. All right, that's what I was looking for. Sorry. 15 times 120. 15 times 120 is 1,800 over X plus $4.76 times X, so 4.7 times 120 is 564. You with me? And what happens to the X's? What's 4.70X times 120 over X? What happens to the X's? They cancel. So I just get 564. So all this is just to get this equation. You with me so far? Now, this is your inventory cost equation. What do you want to do? To minimize, you're going to take derivative, set equals 0, and solve. But before I take a derivative, I'm going to clean them up. And that's going to be paramount on this next test. Clean it up first. So, cleaning it up, I don't like terms on the bottom. I'm going to bring them to the top and make them negative exponents. So this will be 2x plus 1,800x to the negative 1 plus 564. Now, take the derivative, set it equal to 0, and solve. What's the derivative of 2x? 2. What's the derivative of 1,800x to the negative 1? Bring down your negative 1 times 1,800, makes it minus 1,800x to the what? Negative 2. What's the derivative of 564? 0, because it's a constant. So this is my derivative equation. I'm going to set it equal to 0 and solve. I'm going to clean them up. This gives me 2 minus 1,800 over x squared is equal to 0. Does that make sense? I'm going to move this term to the other side. This gives me 2 is equal to 1,800 over x squared. What's my next move? I'm trying to solve for x here. What's my next move? Multiply both sides by x squared. Get rid of your denominator. Just algebra now. So I get 2x squared is equal to 1,800, because that would have canceled. I'm going to divide by 2, and I get x squared is equal to 1,800 divided by 2. You can do that math in your head. What is it? 900. And then what's going to kill off that square? Square root of both sides. What do you end up getting for x? 30. Just to double check. Square root of 900 is 30. I got x equals 30. Does that make sense? But wait, what's the last thing you do to any word problem? Go back and answer the question. Yes, x equals 30, but what's the question here? The questions are, quote, in what lot size and how many times per year should an order be placed? So there's two questions here. What is your lot size? But if you go back and remember, the variable x represents lot size. So what is the lot size? Lot size is x, which is equal to 30. So how many should we order each time? 30 tennis rackets. So the answer is lot size is going to be 30. The other question, though, is this. How many times a year are you going to order? Very good. How did you get that? That's my question. All right, so it's a part of the formula. So, quote, the number of orders per year, number of orders per year was equal to, and it was a little formula that you had over here, the number of orders per year is equal to total order divided by x. So this is equal to total order divided by x. What was my total order that we had? 120 tennis rackets divided by x was 30, and that's equal to what? 4. So you got 4 orders per year. Does that make sense? Do you understand the concept here? What I'm trying to do is to minimize my inventory cost on this thing. I need 120 tennis rackets, but because of the cost of the storage and things like that, I'm going to order 30 tennis rackets at a time, and I'm going to order it 4 times a year. That's going to give me my 120 tennis rackets I need. That's going to minimize my inventory cost. Does that make sense? Look at the next one. Okay? It says this. A furniture store sells 224 coffee tables per month at $1,400 each. The owners estimate that the cost for each $100 increased in price, they will sell 7 fewer coffee tables per month. Find the price per coffee table that will maximize revenue. All right. Now they didn't say anything about inventory costs. We're going back to what now? Maximize revenue. We have revenue equations. Start with what you know. Revenue equation is equal to, we call it big R of x, is equal to x times P. where X stood for the number of items sold, you with me? And P was equal to price. Now, you've got to come up with these equations. That's what makes this stuff tough. So on this particular problem, let's understand what we got here. The furniture store sells 224 coffee tables per month at $1,400 each. So let's run. I'm going to sell 2,224 coffee tables, at $1,400 each. But the owner estimates for each $100 increase in price. You understand what he's trying to go for? You know, to maximize revenue, charge more money. But if you charge more money, you may not sell as much. And you see there's going to be a dilemma there that, great, I got a better price, bigger price, but I don't sell as much. I may not bring in as much money into the store. So if we increase the price, so this price, if we increase would be plus, increase by $100 for in price, they will sell 7 fewer coffee tables. They're going to lose 7 tables. Does that make sense? For each $100 in price that they increase, they're going to lose 7 coffee tables. Okay? So, question. X is equal to the number of tables you're going to sell. Right? So the question is, of course, quote, find the price for each coffee table that will maximize the revenue. So how we're going to get the price, okay, so we're going to figure out the price. What is the price of my coffee table? It is $1,400 plus 100 times, well, what does X stand for? Got to make sure you use the right variable. So we got to sit there and talk about basically how many, so there's going to be a pattern here. So X is going to be the number of coffee tables I sell. So I'm going to come up with a different little variable here. And that variable is going to be this. Let's let, I'm going to pick a unit, a letter, Y. Let's let Y be equal to the number of increase in $100. So Y is going to be the number of times I'm going to increase this $100. So what's my price going to be? It's going to be $1,400 plus 100 times Y. How many times are you going to increase that amount? Does that make sense? If I go, let's make it $200. We're going to increase the price by $200. I'm going to end up losing 7 times 2, which is 14. I'll lose 14 less sales. Does that make sense? So Y is going to be the number of increases in this $100. So this would be the price. It would be $1,400 plus 100 times Y. Y is every time you increase that $100. But then what is X going to be? The number I'm going to sell. It's going to be 224 minus 7 times. Every time I increase $100, I'm going to lose 7 sales. Does that make sense? So if Y was 2, I increased it the $100 by twice. That'll be $200. I'm going to lose 2 times 7, which is 14. Does that make sense? So your price varies in terms of what your price is going to be, and it's going to be based on how many $100 increments you're going to increase by. And then X is going to be the number you sell, which is going to be dependent upon also Y. It's at 224 minus 7Y, where Y represents the number of increases in the $100. So what is going to be my revenue? Putting these two concepts together, revenue, which is equal to R of X, is going to be equal to X times price. But what is X equal to? X is equal to 224 minus 7Y times the price, which is equal to 1,400 plus 100Y. Does that make sense? I'm just substituting it just to get it in terms of that one variable. Does that make sense? Now, what am I going to do with this thing? I'm going to clean it up, take derivative, set it equal to 0, and solve. So if I clean this up, I'm going to actually pull this thing out. 224, just do this very quickly and then I'll let you guys go. 224 times 1,400 is 313,600. Pulling it out, 224 times 100 is, that would be plus 22,400y. Negative 7 times 1,400 is minus 9,800y. And then the last one's going to be minus 7 times 100 is minus 700, but it's y squared. Does that make sense? So my revenue is now going to be 313,600 minus 22,400 minus 9,800 is plus 12,600y minus 700y squared. Now, how do you maximize or minimize anything? What are you going to do? Take derivative, set it equals 0, and solve. Derivative of a constant is 0. Derivative of 12,600y is 12,600. Minus derivative of 700y squared is going to be 1,400 y. Set it equal to 0 and solve. I get 12,600 equals 1,400y divided by 1,400 on both sides. And remember, y is equal to 12,600 divided by 1,400 is 9. So wait a minute. What does y represent? How many $100 increases should he give? 9. So what's the price he's going to sell it? Y equals 9. The price is going to be 1,400 plus 100 times 9. And what does that give you? 1,400 plus 100 times 9, 900. Oops, there's one too many zeros there. Sorry about that. Fast on the fingers here. He should be charging $2,300 for these sets. And how many sales is he going to have? 224 minus 7 times 9 is 161 sales. But that will actually, with that bigger price, is still going to maximize his revenue. Does that make sense? Again, you have to create this new variable about how many increases you're going to have, but this ends up being the answer. $2,300 per coffee table, and he's going to sell 161 coffee tables. Study hard on this stuff. We'll finish the last couple problems next time and move on into Chapter 5, and that'll be on Friday. See you guys then.